So there's the incident ray. The reflected ray is parallel to the principal axis. Ray number 3 leaves the top of the object and travels as if it were going through the center of curvature, but it doesn't make it to the center of curvature. It hits the reflecting plane of the mirror first, and when it does, it hits at normal incidence and it reflects back on itself. So now I need to trace backwards on these 3 rays, which are these reflected rays which are diverging, in order to figure out where the image is going to be. And the intersection point of those 3 reflected rays is going to be the tip of the image arrow. Those 3 rays come together right here. So this is the location of the image. It looks like on this ray diagram that location is about 1 3/4 meters behind the mirror. So according to this rough ray tracing, it looks like our image distance SI is going to be negative 1.75 meters. We still need to make a calculation of that. Now let's actually do the algebra. They tell us several things. They tell us that the object is placed 3 meters from the convex mirror. So my object distance SO is equal to plus 3 meters. It's always a positive number. They tell us that the mirror has a focal length of 2 mirrors. It is a convex mirror, a diverging mirror, so I have to actually put the negative sign in there. Negative 2.0 meters. That's the hard part about this problem. They tell us that the object height is half a meter tall. And now we're asked to find what is the image distance, SI, we're asked to find what is the image height, HI, and we're asked to find what is the magnification. And then we're asked to classify the image. Well, they ask us for the orientation and the type, but essentially nature, size, and orientation of these things are going to be what you're looking for. So let's employ the thin lens mirror equation to help us solve some of these things, and then pull out the magnification equation. 1 over F equals 1 over SI plus 1 over SO. We want to find what is SI. So let's subtract 1 over SO from both sides. At this point you can put in numbers and solve the problem. I'm going to choose to get a common denominator, which is 6 meters, and to put in the numbers. Negative 3 minus 2 is equal to negative 5. So I find that I have negative 5 over 6 meters is 1 over SI. So now when I take the reciprocal of both sides, I get that SI is equal to 6 meters divided by 5. There's my answer. So that's negative 1.2 meters roughly. Now you notice that's different than the 1.75 meters that I said from the ray diagram. The algebraic result is the more accurate result. So the ray diagram is just a graphical technique. You want to go with the algebra when you solve these problems. Now, we also want to figure out what is the height of the image. Since I know what the image distance is, I can use the magnification equation to figure that out. The form of the magnification equation is HI over HO equals negative SI over SO. So I want to solve that now for HI. And I get that HI is equal to negative HO times SI over SO. And I know all these numbers now. I know that the object height is 0.5 meters. I know that the image distance is equal to negative 1.2 meters. And I know that the object distance is 2.0 meters. Now I have to hang on to my signs. You see that I have a negative sign here and a negative sign there that are going to give me a positive answer. And now I put in the numbers. I see that my object distance is 3 meters, not 2 meters. I get an image height of plus 0.2 meters. Now the magnification. The magnification is HI divided by HO. HI is plus 0.2 meters. HO is 0.5 meters, and we can figure that out. The image is 4/10 as tall as the object is. Now let's classify the image according to its nature, its size, and its orientation. In order to find the nature of the image, we look at our sign conventions, and we see that since SI is a negative number, this is a virtual image. Since HI is less in magnitude than HO, then I see that this is a reduced image. And since HI is a positive number, that also means it is an upright or an erect image. So looking at the signs I and magnitudes, we can tell what is the nature, size, and orientation of the image. Let's go to the next example. A 10 centimeter object is placed 46 centimeters in front of a convex converging lens with a focal length of 8 centimeters. Use the mirror thin lens equation to find the image distance and height of the image. Describe the image. Just as a reminder, describing the image means to talk about the nature, size, and orientation of the image. Let's begin with a scaled ray diagram. My object is 46 centimeters in front of the lens. The lens has a focal length of 8 centimeters. Now let's sketch our ray diagram. Ray number 1 travels parallel to the principal axis. It refracts through the far focal point. Ray number 2 leaves the top of the object and travels through the near focal point until it hits the lens. When it emerges, it comes out parallel to the principal axis. You may be able to spot where the image tip of the image arrow is going to be. Ray number 3 leaves the top of the object, travels through the middle of the lens. It does not get bent. The tip of the image arrow is right here where those three rays come together. It's a tiny image. You can see that it's fairly close to the focal point on the far side. And in fact, you're going to see that the farther and farther the object is away from the lens for a converging lens, the closer and closer the image is going to be to the focal point. That's a point we'll discuss in class at some point. It looks to me like this image distance is about maybe 9 centimeters on the far side of the lens. Let's see what the algebra tells us. So let us invoke the lens equation to help us solve this problem. Here are the things we know. We know that the object distance is 46 centimeters. We know that the focal length is equal to 8 centimeters, and this is a positive number because this is a converging lens. We know that the object height is 10 centimeters tall. We're trying to find what is the image distance and what is the image height, and then to classify the image according to its nature, size, and orientation. So let's write down the lens equation, and let's solve it for 1 over SI. And now let's put in the numbers. Now I suppose I could work to get a common denominator, but I think I'm just going to pull out my TI calculator and figure out what this fraction is. In decimals, I get that this fraction is equal to 0.103261 reciprocal centimeters. That's what 1 over SI is equal to. What I want is what SI is equal to, so I'm going to take the reciprocal of that decimal. I get just under 9.7 centimeters for the image distance. Now let's go for the image height with the magnification equation. Let's solve that equation for the image height, and now let's put in the numbers and substitute them into the calculator, and I get negative 2.11 centimeters for the image height. Now, nature, size, and orientation. The nature of this image is real because the image distance is positive. The size of the image is reduced because the absolute value of the image height, just over 2 centimeters, is less than the object height, 10 centimeters, so it's reduced. And the orientation is inverted because the image height is a negative number. So this is a real reduced inverted image according to the algebra, and our ray diagram seems to confirm this. So for the optics part of this lesson, we are finished. Now we move on to radioactivity. It's a little puzzling to me why it is that your authors choose to introduce radioactivity here in lesson 54, because it's not going to be until we get to lesson 69 that you actually use the information from this lesson. But this is when your authors introduced it, so this is when we're going to discuss it. Basically, what your authors are interested in having you know is that there are 3 types of nuclear radioactive particles. They're the alpha particle, the beta particle, and the gamma particle. And we're going to take a look at what those 3 particles look like in their nuclear notation, because they'll be used in nuclear reaction equations in later lessons. When we say that an atom or nucleus is radioactive, what we mean is that it's unstable. we mean that the nucleus is going to transform. It's going to change from what it is into something else. And the way that it does that is by giving off these particles, or it may be induced to change by being bombarded with some particles, say like protons or neutrons or electrons or some other subatomic particle, and in the process the nucleus may be compelled or encouraged to change by its interaction with these incident particles. But natural radioactivity consists of three types: alpha, beta, and gamma, which are A, B, and C in the Greek alphabet. The alpha particle was discovered first. It is now known to be a helium nucleus consisting of 2 protons and 2 neutrons. Now, if you'll recall nuclear notation says that you indicate the atomic number on the bottom as a subscript and the mass number in front as a superscript. So these alpha particles will be indicated as a 4-2 helium, or sometimes you'll see it as a 4-2 alpha particle. Those two things mean the same thing. Next comes the beta, and the beta particle is a bit more strange. It is a bit more variable than the alpha particle is because there are two types of beta particles. One of them is called a beta minus, which is an electron. The other is a beta plus, which is a positron or an anti-electron, basically antimatter that is a particle that's identical to the electron, but it consists of positive charge instead of negative charge. The charge on the electron is -1, so you may see this indicated as E for electron, -1 for atomic number, and a mass number essentially of 0 because the electron is roughly 2,000 times less massive than protons and neutrons are, so it has a mass of essentially 0. Sometimes you'll see this indicated as a beta with a -1 subscript and a 0 superscript. Both of those are beta minus particles. The other is a beta plus particle. This is the positron. It will be indicated sometimes with a P for positron. It'll have a +1 downstairs and a 0 upstairs, or you may see it written as a 1, 0, the 1 being the subscript and the 0 the superscript. Those are the two types of beta particles. Finally, there is the gamma. The gamma is basically a high energy photon, and photons do not have mass. So when we talk about the gamma particle, basically what's going to happen is that when a nucleus throws this off, it's just throwing off high energy. So it has a mass of 0 and a charge of 0. This is a high energy photon. That is basically all that's introduced in this particular lesson about radioactivity. An important point that your authors point out that I have not yet discussed is the penetrating power of each of these types of particles. Alpha particles are not very penetrating. It doesn't take very much to stop an alpha particle. So if you're trying to shield something to protect it from alpha particle radioactivity, then it's pretty easy to do. Beta particles are less easy to shield against, but they are, I would call them, medium penetration ability. So if you're trying to shield yourself against beta particles, then you have to work a little harder than you do to protect yourself against alpha particles, but not much harder. On the other hand, gamma rays are very highly penetrating, and it's difficult to shield against them. It turns out that gamma rays are used in medical diagnostic or medical treatment of various sorts of things. So you may have heard of a gamma knife, or you may have heard of radiation therapy that cancer patients go through. And basically what's happening is these gamma particles are focused on a certain place where the cancer is located. That cancer is bombarded by these gamma particles. The gamma particles go in, they're very highly penetrating, and they essentially kill the cells. The mechanism is not something that we're going to discuss, but you should recognize that these are radioactive particles.